Hello. So today I'll present on the random distributed scalar encoder. So it's a better version of the scalar encoder that we used to have previously. I'm by no means an expert on the subject. I just learned about it in the last week. So if there are any mistakes in what I say or what I'm presenting, feel free to call me out on it. Fortunately, we have the person who implemented it here, so I'm sure my mistakes will be caught. Okay, random distributed scalar encoder. So this is the agenda. I'll let you take a look so you know what you're getting into. All right, so first let's take a look at the scalar encoder as we had it before this one. So the basic scalar encoder, the point of the scalar encoder, as a review for especially people who are watching at home, is that you have a scalar, you have a value that you want to encode in a sparse distributed representation so that these spatial pooler can use to learn spatial patterns, and then temporal pooler can use to learn temporal patterns. So we want to take a scalar value and want to encode it in bits in a sparse distributed way. So the way we did it before is we would we took a scalar and we would bucket it, we represent it with a set of bits that are adjacent. And the next scalar that we wanted to encode, we would represent as with the bits that were adjacent. So you can kind of see, let's say this is the value 3, and then this would be the value 4. Now it doesn't necessarily have to be one full integer value ahead. You can, the delta between two different adjacent scalars can be anything that you pick, and that's determined by some parameters that I'll go over later. But basically, let's say we want to encode each integer as a separate bucket. So these 3 bits would represent the bucket that represents 3, and this would be 4. And the reason we had the bits overlapping in this way is that the scalar value 3 and the scalar value 4 actually mean something conceptually. They actually are similar in a certain way, in a way that 3 and 10 are not similar. So you want those adjacent scalars to be represented in a way that they share some overlapping bits, so that the spatial pooler can learn the representations and the bits, and use the bits that they share to understand how similar those scalars are. So I'll go over the objectives of the encoder in a bit, but this is how we had the scalar encoder previously. The problem with this is that, notice you have to specify the min and the max for what scalar values you want to represent. And when you hit the max, so let's say the max is 5, or let's say it's 7. So this is 3, 4, or 6. 3, 4, 5, 6. Any value beyond 6, like 7, 8, 9, 10, they all end up saturating the right edge, and they end up being represented with the same bucket. So now this spatial pooler has no idea whether these 3 bits are representing 6 or they're representing 10. So when you specify the min and the max, the problem with this encoder is that you cannot represent anything beyond the min and the max, because they will just end up being represented by the same values as the edge, as the boundaries. Okay, so the objectives of a scalar encoder, let me skip over for a second. So the objective of the scalar encoder, when we're designing a scalar encoder, the main 2 objectives are that you want to represent each bucket with a number of bits, and you want it to be a sparse distributed representation. So you want it to be sparse, and you want the bits to actually have some conceptual, contain some conceptual meaning about those things that they're representing. In this case, scalars. And because conceptually 2 adjacent scalars have more similarity than 2 non-adjacent scalars, you want adjacent buckets. Buckets are basically a bucket of scalars that is being represented. You want adjacent buckets to share many bits, and you want non-adjacent buckets to not share any bits. So that way the spatial pooler can learn the correct representations. So why do we need to create a new scalar encoder than the basic one? So we already talked about some of the limitations of the basic scalar encoder. The new one, the random distributed scalar encoder, it solves some of these problems. So the problems of the basic scalar encoder is we talked about saturating representations. You have to decide on the min and the max. So that's a problem because, especially with streaming data sets, you don't really know what the min and the max is going to be, and that's the whole point. is that you don't know what the data is going to look like. It should learn to represent the data, whatever it is. Whereas if you have to decide on the min and the max, then you've defeated some of that purpose.
And you always pick wrong.
And you always pick wrong, that's right. So it's not going to perform very well if the data ends up having outliers or having going outside of the boundaries that you thought it would have. You also can't change the range of the encoder at runtime when you realize that it was wrong. Because if you do that, then the things that used to represent something now represent, the bits that used to represent some buckets now represent different buckets, and you've lost some learning that had occurred.
I think we have an encoder, adaptive scalar encoder maybe, that does that. Every time the min moves, it sort of remaps everything, and then you lose some of the learning.
Yeah, that's right. So the adaptive version does that, and it has the advantage that you don't have to decide on the min-max up front. It'll determine that based on the statistics of the data, but then every time it changes the range, as in point 3, you lose some of the learning. So that's a downside to it. So the random distributed scalar encoder solves these problems, and we'll see how it does that. So here's the algorithm for the random distributed scalar encoder. I'll go through it with you. And we'll do it kind of conceptually. Rather than reading this, try not to read this. I know it's on the screen. This is kind of for your reference, but let me go through it, a mental picture. So what we do is we start with the first bucket, okay? Let's keep it simple and say the first bucket is a bucket centered around the value 0. So imagine a scalar line, a number line, and we start at 0. That's the center. Okay, it should be fine. All right, so let's start at 0. So imagine a bucket centered around 0. That's the first bucket. And for the first bucket, we select among the number of candidate bits that we have a bunch of bits that can represent all of these different buckets, right? So of those bits, we select the number of the bits randomly. And those bits that have been randomly selected, those represent the first bucket, okay? That's centered around 0. Now, let's say we want to represent the value 10. So we have to move from the bucket that we have towards the right on the number line. And we need to move, as we move, we need to generate buckets. Because we don't have buckets, we don't have bits representing buckets in between. We only have bits representing the first bucket, which is at 0. So we start moving towards the value 10 on the number line, and we generate buckets along the way. And the way we generate buckets is, so for a new bucket that we do not have bits representing, we take the previous, we always keep a map of which bits were assigned to which buckets, all right? So then when we move to the right to generate a new bucket, we make a new set of bits to represent the new bucket. And we do that with the following bits. We take all but one of the previous bucket's bits. So we take the previous bucket and all the bits that it used to represent it. We take all of them except one bit. Then we randomly select a bit from the pool of the remaining bits. So the pool of bits that are not used to represent the previous bucket, we select one of those bits, and we combine those bits into to represent a new bucket. And we do that because remember we wanted adjacent buckets to share the most number of, to share bits. We wanted non-adjacent buckets to not share bits. So basically when we move to the right by one bucket, we want those two buckets to share all but one bit. Right? So hopefully that makes sense. So now we generate buckets this way. We keep sharing bits between buckets as you move towards the right, and you keep dropping off bits as you move along the buckets. And so you keep doing that until you reach the bucket that you want to represent, and then now you have a bunch of bits representing that bucket, and that's your answer. And for when you're assigning a scalar to an existing bucket, just look up which bits are assigned to that target bucket. You calculate which bucket that scalar would fall into, and you look up which bits are used to represent that bucket. So that's it, and here's an example. So here is, just like in the previous picture, I should have probably described how the previous picture worked, but here's time. So imagine that we're representing the values 0, 1, 2, 3, 4, okay? And we're representing those scalars, and we're moving forward in terms of scalars, and this would be 0, 1, 2, 3, 4, 5, right? So as you move forward in time, you're trying to represent increasing scalar values. These are the bits that represent the bucket. These are the available bits. So you can see there's 8 available bits with which to represent all the buckets. So the first bucket we randomly select, right, as per the previous algorithm. So we select this, this, and that bit to represent the bucket 0. Now let's say we want to represent the next bucket because we want to represent the value 1. we want to generate a new bucket, right, based on the previous bucket. So we select two of those bits that were used to represent the previous bucket, right? These two, and because we want to select all but one, and then we randomly select among the remaining, which would be this, 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 and this. We select one bit, right? We'll select that one. So now these 3 bits represent this bucket, and you can see that these 2 buckets share 2 bits, right? And they don't share the last one. So these 2 are uniquely represented by these bits, but they also share some bits. They share all but 1 bit. And you can see that pattern follows. So these 2 are shared there, and this one is not. And as you move forward, that's kind of how it generates. Now, you can imagine that as you try to represent more and more scalar values, right, you might end up reusing some bits that were used to represent a previous bucket. So that's what ends up happening when you have a limited number of bits to represent buckets, and you're trying to generate an infinite or a large number of buckets. So it ends up saturating the representations that each bit ends up taking.
So you could have the same set of on bits representing different scalar values at some point in time.
And that's a failure case, but
that's a failure.
The implementation gets around that.
Yes. So that's what ends up happening when you. So this is a kind of I shouldn't use the word adaptive because it means something else in a different context. It's basically during runtime it's generating representations, and it has a limited capacity because there's a limited number of bits with which to represent buckets and a potentially infinite number of buckets, right? But it's smart about that saturation occurs only after a lot of buckets have been represented.
And if you think about the numbers that we actually end up using, there's a lot of room here because this is an artificial example, but typically we have several hundred bits available, and our W is 21 bits on at a time. And it's okay to have a couple of bits that are shared, that are colliding with another representation. That doesn't cause any problems with the SP.
Yeah.
And so
because the SP is also fault tolerant.
Yeah. So if you couldn't have any bits colliding, then you'd run into a problem. It would be very similar. But because you're allowed to have a couple of bits that collide, you can have thousands and thousands of these representations.
So Surpur, can you do it in your head if you added another bit to n? How many more could you uniquely represent before you get those in?
I don't know.
But how does it scale?
Yeah.
Let's talk about the properties.
So the question, well, it depends how many bits you're allowed to overlap.
So here in this example, we have 3 out of 8, and we want no overlap between.
If you want no overlap.
Or well, here we have.
If you want no overlap, there's very little room because it's basically very similar to what we had before. You can have
duplication.
It scales linearly if you allow no overlap, because if you have one more bit, there's only one more bit you can add. If your tolerance is 0, so then that'll scale linearly. But if you're allowed to have 1 bit of overlap, then you have another degree of freedom. If you're allowed to have 2 bits overlap, you have another degree of freedom. So probably scales quadratically or as a cube.
So is it actually storing every number that it's encountered, so it knows which bits it maps to? I'm just wondering of the memory footprint of this thing. If somebody's using a really big portion of the number scale.
Yeah. It doesn't store all the numbers, it stores all the buckets.
And the bucket has okay, so I think I missed it somewhere.
Yeah,
to be clear, I should have described
because when we talked about buckets here, we're talking about, well, here's a bucket represents 0, here's a bucket represents 1.
Yeah, in fact, you can have a bucket representing the range 0 to 2, and then the next bucket would represent range 2 to 4, and then 4 to 6. And so a bucket is just a grouping of scalars. It represents a range of scalars. And so, in fact,
it's a range of scalars that have the same representation.
That have the same representation. So yeah, 0 to 2 would look the same to the SP as 2 to 4 in that example. So in fact, here is my next slide was going to be describing what parameters control what a bucket looks like. So n is the total number of available bits. In the previous example, it would be 8, as you saw. W is the number of bits representing each bucket. So in this case, it would be 3 on bits, and that represents 1 bucket. And R is how wide a bucket is. R is resolution. So as I said before, a bucket is a range of scalars that are all represented in the same way. They all look the same to the SP. So depending on what R is, it'll control how much grouping there is of the scalars, basically. So if you have a large R, then let's say the difference between a bucket that has about, let's say R is 10, so 0 to 10 is represented by the same bucket. So the same set of bits represent all the values from 0 to 10. Then 10 to 20, then 20 to 30, those are all individual buckets. That's a high R. A low R, let's say a R value of 1, so 0 to 1, 1 to 2, 2 to 3, all those ranges would be individual buckets. So the SP would be able to distinguish between those ranges.
Numeric line is infinite. I mean,
yeah, so there's some limit, and that's controlled in the code. There's actually a maximum number.
So there really is still a minimum and maximum.
Yeah, but
it's dynamically generated rather than.
Well, no, it's not dynamically generated. I mean, you run out of memory.
No. What I mean is that instead of me going, well, this value is only ever going to go from 1 to 50, we let the stream determine that. And at some point, we fill up that table, and that's it. We've reached a max, and that max might be 330 or 500 or whatever. But
so it's possible to do a version of this with constant memory footprint, regardless of the number of buckets you have. We sort of have a static way of looking them up, but we did the math out, and that would make it take longer, and the amount of memory that this uses is tiny for any reasonable number of buckets. So.
But I think we still created the math.
You still have there's still an implicit min and max. You don't have to. Generally speaking, the range is pretty large, so you don't need to worry about it. But yes, there is an implicit min and max.
So for example, let's say you have some number R, right? And I think we're still trying to maintain the relationship that numbers or buckets that are near each other should share a lot of bits in common, right?
Yeah.
But if, let's say the data is jumping with really big leaps many times the size of R, right? And so we haven't encountered some of the data that was close. We're encountering data that's really far apart.
Yeah.
Then later, when you get data that's happens to be close, we might be out of buckets, right? All the buckets are already used, and
well, the data that's when you
and then things that are far apart actually appear like they're near apart, like they're near each other.
So there's
because as you run out of buckets, you have to.
Well, one of the properties you lose in this is the ability to immediately tell the distance between two numbers without essentially walking through the number line. Because you can't say that this set of these two non-overlapping set of bits are any farther apart than any other two set of non-overlapping bits.
But that's true with the old scalar encoder too.
No, you can if you know you have bits at the beginning of the number line and bits at the end of the number line, you can literally look at the indexes, and that is a distance representation.
Same here. You can there is a mapping from bucket indices to the bits.
Yeah.
So
the way I described
you could do a reverse mapping too.
Conceptual. I think. Here I have a question actually. So I described it as when you get a value over here, you have to walk through and generate buckets as you go.
Mm-hmm.
Could you just like go and generate this bucket and then, as necessary, fill out the buckets as you get values that need to be represented?
You need to maintain this property that all the ones in between have to still share. So so you actually have to walk through and generate in between, unless there was this static, the idea of being able to do a static.
If you do it intelligently, you have a random set here and a random set here, and it doesn't matter whether you walk through or you generate them, they're both going to be random and they're not going to share bits.
Right.
Then only when you get an adjacent one would you have to calculate the overlap. And
but you have to do it in a way that, exactly.
When you meet in the middle, they'll actually.
You have to interpolate so that it works all the way through.
Okay.
So the easiest way is just to generate.
So it's actually, if there is a big gap, you're actually reserving bits for the buckets that would have been implicitly or explicitly would have been in the
Exactly.
So later, if these values do show up, there will be space for them.
In fact, they will already be generated.
There will already be a bucket for them.
Yeah. So it won't run into the exact problem you specified, but there is still an issue here of, there's only so many so much memory and so much room for buckets. And so if you have data that's really far apart, like exponentially far apart,
right.
This is not a good solution. But neither is the old Scalar Encoder.
Well, it depends on how you decide on R.
Yeah.
So if the data is very wide, you want a larger R, and that's the only real parameter that you control.
I want to jump in. So I think there's two cases. There's a case where you have a really big range, but like uniform data, in which case you just need to make sure your resolution is correct. And then there's the other case where it's non-uniform data, in which case you may need like a log encoder or something like that.
Yeah. So this sort of assumes a reasonably uniform encoding or distribution of
So in a way, you kind of still have to know what your data is going to look like in the future, but we actually don't know what the data is going to look like in the future.
No idea. Yeah.
And so you could still end up in a lossy situation, right, where we're losing learning because too many things start mapping to.
Yes, but the point at which that happens is much further out than with the old Scalar.
Yeah. These issues would be there for the old Scalar encoder as well.
So there's a separate separate thing of, okay, how do we do a really good adaptive encoder that adapts to the statistics of the data? And that's still an open question. I think we have an implementation in NuPIC, but that's still to be really proven out in realistics.
So if that one is proven out, would we choose to use that over this, or would this still have advantages?
If the other one has no disadvantages, then yeah, then there would be no reason to use this.
The other one would be more advantageous,
yeah.
right?
But I think they're two, actually, they're two independent ideas.
Mm-hmm.
One is how do you allocate the bits? Previously we used to do it all contiguously. The idea here is it could be random.
So it doesn't need to be.
Right, and then the other one is how do you represent the statistics of the input? They're independent ideas. If you could figure out how to represent the statistics of the input or estimate them, you can still use the random encoding strategy.
There are reusable elements here that could be used
exactly.
with other encoders.
Yeah, and they're not tied.
And it's impossible for an adaptive encoder to be as good as a non-adaptive encoder if you know the min-max. That's just a hard fact.
Sure.
Yeah.
Yeah, because what I'm concerned about is like when people start using custom metrics and say they're doing something and one of the things they're measuring is say sales, and they get the typical hockey stick and suddenly we go from having had a range of 0 to 100 for a day to suddenly, oh look, we made 10,000 sales because we finally did that Super Bowl ad.
Yeah,
but I think
we don't want to get too much into grok specific stuff here, but that's definitely an issue, and it's like, but the old Scalar encoder would have crapped out long before.
Yeah,
it gives us more room.
Yeah, we have more leg room. I guess we're at some point we're going to have to think about triggering like relearns, where we can say, okay, this model has this particular model that we're doing was great, but now we know that our range is 50x what we were initially doing.
What's the the current MW? What is the theoretical maximum number? Because I don't think we reached that. It's a very large number. So.
It's pretty large. It depends on the number of how you set.
It depends on your range.
Like I think the W is 21 and is 1,000 or something.
No, I think N is
400.
400? Yeah, somewhere around there. It's a few hundred. The other problem is if you make N too large, the spatial pooler gets slower and slower because you have more, the number of bits for each column grows, and so there's a practical issue.
An idea is maybe R could be dynamically decided based on the statistics of the data as it moves forward. So initially it's small, and then if we get an outlier, then you increase. And you choose an R based on where you are on the number line. And so if like the next 1, 2, 3, then 10, you want the R to be larger, and then 100 you want it to get even larger. So then it's still adjacent bits and all that stuff, but then you're not representing so many.
No, because I think from what you're saying, you wouldn't change anything you've already learned.
Yeah.
It would just be the new stuff.
The new buckets that are being allocated would be larger.
Well, maybe too late by now. Maybe they're all used up already.
Then you get an outlier, right?
Yeah, but there's a fair amount of room here.
Yeah, there's something.
All right, cool.
Fortunately, unfortunately, these are all things that we would have had to deal with the other thing anyway. So, just additions onto this. I'll get to why this is better. But okay, so those are parameters, and I think those should make sense. In fact, R is a little confusing. It's like that in the code, but it's technically inverse of R because it's not resolution. As you increase the resolution, you're actually decreasing the real resolution.
Yeah.
Right? Because the bucket size is getting larger, so what the SP sees is now smaller resolution. If that makes sense.
Yeah, maybe we should change.
Should rename it.
Rename that
Oh,
to
name
like
changes
spread
are
or
painful.
something.
I always thought of R as range.
That's good.
But range is really from the smallest number to the biggest.
Range of your bucket.
Of a bucket.
Bucket range, okay.
Start time.
So it's B, R.
So we could just change the comments.
Make sure I didn't miss anything. Okay, so now some intuitions, so we get a good feel for how it's working. Each bit is contributes to representing multiple adjacent buckets. So that's already the case. We want that to be the case for when the buckets are adjacent, when the scalars are adjacent. But then as you create more and more buckets, the chances of selecting a bit for a new bucket that already represents an existing non-adjacent bucket increases. So that's the failure case, is you want the bits to represent multiple adjacent buckets, they want overlap on the bits, but then as you get farther away and they're not adjacent anymore, you don't want that bit to turn on for buckets outside of that range. But if you have a small n and a large r, a small n and a smaller r and a larger data set, or a wider data set, then you'll end up with the failure case where a bit is representing buckets outside of that range. And that'll happen more and more as you increase the range of buckets, as you generate more buckets.
So hold on. So for example, let's say you've used up the buckets. Now, but you still have different numbers coming in that did not map into those buckets. So then the algorithm would pick somehow arbitrarily which bucket represents that number that is beyond the
outside of the range of created buckets?
Yeah.
Well, no, it would walk along to.
Right. But let's say all the buckets are already used up, and this number is outside.
Oh yes. So it would.
Is that what we're talking about?
Yeah, that is what we're talking about, and it would randomly pick some of those bits, even though they've already been representing buckets. It would pick them to represent the new buckets as well, and so you'd end up with the bits representing more than just adjacent buckets. Fortunately, the SP is fault tolerant to that, so these bits would now represent multiple non-adjacent buckets, but the SP would somewhat, it's more like loose with how, it doesn't require the buckets to represent just one thing. It would just get worse at spatially grouping them correctly. But it would happen progressively.
Would the choice of the bucket for this number that's now outside of the range of all the allocated buckets, would the choice of the bucket still have some kind of semantic closeness to other? For example,
if you're going to
so it's not completely random, right? It will still be close to other.
It's close to the other buckets near it.
In the area.
Yeah, that property always holds.
Okay.
But also to the previous level, right? It's like if you say you have the first 10,000 fit in the first outer bit, now into the median number range. Now the median range is going to use the same range as the outer range.
No, because it's randomly selecting the bits, not based on the previous range that.
No, but I'd say 1,000 was bucket 5, and 1,001 is bucket 6, and so forth. Right. But now I have a million. That's still bucket 5. And
No, there's no bucket 5.
That would be bucket million, and
bucket million.
Those bits would represent bucket 5 and bucket million.
Right.
And then bucket million and 1 could pick any other of the bits. It doesn't have to be bucket 6. It could pick what used to represent bucket 2. Because it's randomly selecting, it's not selecting, it's randomly selecting from the pool of remaining buckets. It doesn't see what buckets they're currently in. And that's actually why why those bits end up representing multiple buckets. Because it's not looking, with a caveat, it's not looking for buckets, for bits that are not representing.
So you don't get the failure where, for example, let's say all the buckets are used up, but the numbers that are coming in keep increasing, for example. So you don't get the new numbers all being represented by the same bucket that represented the last, let's say, highest number. So let's say you're at the million billion, and you've used up all of your buckets, and now you're getting higher numbers yet. Are all of those higher numbers going to map now to the same bucket, or is there's still randomness in there?
They're still randomly selected from the other bits. Yeah.
But they're still going to be maybe closer to other high numbers.
Yes,
As opposed to being close to low numbers.
Yeah.
Also,
Only within us. No,
the,
usually it won't be close to the high numbers. Only if we're going 1, 2, 3, 4, if the resolution is 1, and let's say W is 21, 21 of the numbers will be close to each other, but if you're more than 21 away, there's no relationship anymore.
Yeah.
Oh, okay, so you
imagine it's kind of like a fog of war idea, where like when you're playing a game, you can only see within a map region, and it like there's a fog, and then you can't see outside of that. When you're moving along the range, you're just seeing what you're seeing, and nothing else is affecting that range.
So numbers in that region of the numeric scale, they'll still have that property that they will be close to each other, that their buckets will have overlap.
Within that 21.
Within that fog.
Right,
yeah.
okay.
Yeah.
Okay.
Yeah. Okay. I hope that.
But just to be clear, going from 1,000, 1,001, 1,000 to 1,000,000 is not a good use case of this.
You probably run out of memory in generating the buckets. Okay, so so we talked about that. Pretty much the SP, as you get more and more buckets and you're saturating the bits, the SP it becomes harder and harder for the SP to tell the representations apart. But it happens progressively and smoothly, and learning is never disrupted, never lost, because the representations never change. They just the bits end up representing more things than the original. They don't end up representing different things. That's the advantage. And so the sort of representations become more blurry over time, but they never get lost. So that's the advantage, and it happens smoothly and automatically. So it's kind of elegant in that way. So intuitions with the parameters. So the bigger the n, the less likely, the more bits you have available to represent stuff. So the less likely you'll have overlap in non-adjacent buckets.
And the slower the system.
And the slower exactly. That's the downside, is the slower the SP would be. The bigger the W, so W, if you remember, is the number of bits that represent a single bucket. The bigger the W, so the more width you have, the more overlap there will be between adjacent buckets, right? So that means SP will attribute more similarity to between those buckets. So you'll get more, I guess, spatial pooling on those buckets. The bigger the R, the more scalars will be grouped together in buckets. So again, it's the range of the buckets. So if you have a large R, then 2 and 3 will be represented with the same bits. If you have a small R, then 2 and 3 might be represented with different buckets. And so the spatial pooler will be able to tell them apart. Okay, and so results for our data sets, the random discrete scalar encoder is better, because if you think about it, if you set the min and the max correctly for the basic scalar encoder, and it fits the data, then the basic scalar encoder is good. Like, it works exactly as we want it to work. The random discrete scalar encoder works almost the same. So there's a chance for bits to overlap with to represent multiple non-overlapping buckets within that range, but that chance is very small, right? Especially if you set R correctly. So it's about the same.
We have constraints in the code to control exactly how much overlap you're allowing.
That's right,
in those
yes.
Cases. So actually,
so there's an
control it
optimization
precisely. Yeah.
Okay, so in fact there's optimization to prevent that from happening if the number of buckets is small enough that we can uniquely represent them with the bits. So in fact it'll perform just as well within that range. Now outside of that range, since the basic scalar encoder will saturate the edges, the random discrete scalar encoder is strictly better, because it will be able to uniquely represent those things, though you'll have multiple bits per representation. Multiple representations per bit, sorry. So the basic one will be worse than the random discrete scalar encoder in the case where the boundaries are what you did not expect, which is usually the case, actually. And that's why it generally performs better for our data sets. It's easier to use and configure. The user with the basic scalar encoder has to specify the min and the max, whereas in this case they don't have to. So they would have to specify min, max, and W, which is implicitly controlling that resolution or range that we were talking about. In this case, they just have to specify the range, the resolution, and hopefully, maybe we can think of potentials where that resolution is also set dynamically based on the statistics of the data. But it definitely does not have to set min and max, so it's easier for the user, which also means it's better performance-wise. So we believe that there's no reason to use the basic scalar encoder anymore. We can always just use the RDSE, other than the way I use it just now, which is to explain how it works, because it's easier to conceptualize the basic.
It's much easier to see.
And easier to see, yeah.
So did we do tests on, I mean, if we're willing to allocate 400 bits to these representations, plus the memory overhead, did we test to make sure that you don't just take the 100 some bits, add 150 on every side, and allow that for padding to, you know, we do a 10%, 20% pad, but if we have 150 additional bits on each side, just use a regular scalar encoder and not worry about it.
Yeah, you'd have to do a 10x at least, because the amount of room in the random encoder is much more than...
Yeah, but do we need that? That's the question. Is there any evidence we actually need it? Because
yeah,
we don't have any hard numbers here on capacity versus the statistics of the data that we've actually looked at.
You're saying we always close enough.
Yeah, we can get within...
Well, this isn't any worse, right? This is it.
Well,
you can still... The big downside to that thing is that the system runs much slower. If you double or increase, if you add 100 more bits, it actually has a pretty measurable impact on the spatial pooler. Because
but that's what this does.
No.
No. This has more capacity in the limited
It does. It has no impact on the...
But we're actually using 400 bits. Like, that's the implementation. So...
Correct.
So if we're willing to pay that penalty anyway, and the statistics of our data,
I see what
we
you're
get
saying.
close enough,
yeah.
Why bother with a new
Yeah,
implementation?
if we could have otherwise gotten away with, let's say, 100 bits, let's say with the scalar encoder, we only needed 100 bits. You're saying, well, which, you know, then why not just use 400 and have a 3x range?
Yeah.
And do we have data that, I'm pretty sure we have data, but we can check. It's just, you're saying, you know, can we guess min and max within a factor of 2 correctly? That's essentially what it amounts to.
Yes.
That's the question.
Yeah.
No, but now we have this. This is strictly better for the same number of bits, right?
Well, this is a more complicated implementation. So
Correct.
the other one is simpler.
But then it's easier to configure also.
Yeah, it's much easier
for the
to
user,
configure.
because if the implementation is proven, then the only thing remaining is for the
Well,
user.
the R estimation is still something that you have to deal with, right?
You have to still do it, but it's you have to do it anyway in the previous case.
Yeah.
So you don't. It's
So,
not like
I mean,
it's a new thing.
If the status quo is you have to do an estimation of your underlying statistics, right? So you're gonna be wrong one way or another.
Right.
You still need the min-max for that.
Yeah, but you don't need an absolute min-max.
You don't need an
a
absolute
guess.
min-max.
This is much more tolerant.
You can. Another thing you can
so-
do is you just look at the first few data records, and you can decide what the resolution is based on that.
Yeah.
Versus because the information about resolution is encoded in the difference between the records, whereas the min and the max is encoded in the entire data set.
That's we see bimodal distributions all the time, and there's no it's the same problem. So you have to look at some portion of your data set to make an estimation of R or min-max, either way. And the question in my mind is, do we actually have data sets that fail with a scalar encoder, but with a much larger representation?
Yeah, I think it's a good question. We don't have a definitive answer to that. Okay. It's just it's a good question. Can we, in realistic situations, can we come within a factor of 2 of the true min-max?
Yeah.
I don't know.
And I think that, something that people who want to actually use this, and I'm sure there are lots of people who will because it's really cool, will want to know, like, how big does my N have to be given, my general understanding of the statistics of the data or similar data.
Well, in the general case, we swarm over N, so you don't know until you've swarmed. And so, we would swarm up to N of 500. So in the general case, it's a stronger case for this.
Interesting.
And in swarming also, you have to set the min-max, otherwise the swarming didn't work well. So this is actually still much easier.
You have to set the min-max for swarming on which min-max? The range of swarm
for each
parameters?
each scalar encoder you use it.
Yeah.
Are you saying you have to set the range of the swarm, or the range that it looks for, and it does not swarm over those?
It doesn't swarm over min-max.
Oh, okay. So you have.
But Because I think from the user point of view, people are going to start with.
You could, but Swarm works on a fixed data set, so there's no point. Really.
Like, I think people are probably going to start with the examples that don't swarm. They're going to start with, say, the hot gym example where we have parameters, but they can specify which encoder to use at that point. And the question is, do the statistics of the hot gym data lend itself, let's say that you didn't know the statistics up front, is that a good example of where the scalar encoder fails? Or is it, is there a better example where we can say, well, if your data set looks like this, it's clearly better to use RDSE?
I think it is because, from a practical standpoint, whenever people have come to me and said, oh, the data set is not, I'm trying a new data set, it doesn't work well, the #1 reason it doesn't is because they didn't set min-max correctly. It's always, even though, yes, in principle they can do it, they just don't do it. And so this, but oftentimes it's a small change or maybe a fact, and so this really, I think, ameliorates that situation. So from a practical standpoint, yeah, I think this would be much better to use. You've gone through this too. It's like the #1 response. It's like with Windows, the #1 thing is, have you rebooted your system? With with NuPIC, it's like, have you set min-max properly? It's like that.
What happened when you reset your min-max?
Min-max is like the blue screen of death for.
So then I guess the question will be, is the default resolution and the capacity of the default RDSE sufficient for most people? And given a 400-bit wide encoding, it probably is, given the huge capacity.
There's quite a bit, and it's you can change it. It's a parameter. No, it's not like
but to make it easier,
you're pretty much always going to want to set the resolution.
Like, yeah, you have to still set the resolution.
But that's where the capacity question comes in, because if your resolution is 1 or resolution is 0.5, for example, is that good enough with 400 bits to take into account a data set that only goes from 0 to 10, and as well as one that goes from 0 to 1 million? And
so that
I don't know.
That's actually
either one. Like, is 0 to 1 million representable cleanly with an RDSE of 400 and
with what resolution?
With resolution of 0.5.
No,
no,
I don't think so. I don't think it has that much room.
Okay.
Because we limit the amount of overlap. You could if you tolerate more overlap.
So you have a good intuition of that, but I don't. So it seemed to me like it would have a good representation. So it might be useful to have
I don't think it has that much room. I think it's more like quadratic, or I think I have it set to like you can have 2 or 3 bits of overlap. Again, it's a parameter, but most people wouldn't set it. I think you can tolerate a couple of bits of overlap. Yeah. If you allow more collisions to occur, then you have a lot of room. And you have much more room.
Yeah, want to avoid that as much. I mean, that's a good lead into my take-home question to you guys was going to be that the RDSE is not an adaptive encoder. It doesn't learn the statistics of the data and doesn't allocate buckets according to those statistics. It's all, the parameters are fixed in how it allocates buckets. Could we come up with a way where we generate the buckets in an intelligent way to mitigate the issues with a too small resolution or too large resolution, and have it determine that at runtime as well? So then it would be fully just let it loose and let it figure out what, because again, that hockey stick image is a very good one. You want to represent all the ones at the flat line, and you want to represent all the differences in the spike, and you don't want to lose the flat line just because you got the spike. Could we allocate those buckets more intelligently without a fixed resolution? And what would the implications of that be? That's something to think about, and it's open for experimentation.
Yeah. That'd be a great project for someone to do.
Yeah. Thank you. And if you have any questions, we can all talk about it together.
Here's one question.
Yes.
Would it be fair to say that the old basic scalar encoder was inefficient because it was kind of oriented towards my human visual system? I could watch it change, from min to max, the one scroll across to the right, where now the computer does the mapping instead of a simple, my visual system can tell. So I can't tell what the SDRs mean anymore, but the computer knows the same pretty much. Yeah. And I can just rely on it. It's a much more efficient path.
Yeah, I think that's a good, before we constrained it to be sort of visually makes sense, but
Yeah.
the computer doesn't have that constraint. So this is probably not at all biologically
I don't think that that makes it less efficient though.
Yeah, because the bits were had to be contiguous.
No, because you could do a static mapping from the contiguous one to a random one, and you wouldn't. It would be the exact same functionally, but you would lose that property. So I mean, you're not like losing bit combinations that you wouldn't have otherwise.
No, you
You
lose.
do.
You can only build one to the left, one to the right.
You still have.
The random, you can use any other bits.
Yeah, but that's the only new combinations you get have collisions.
Well, the old one, you were, if you had an n of, n and w, then you're restricted to n minus w plus 1 possible positions.
And you still have the
And that's
same
because
number
you're-
without collisions. Right?
I'm not following.
I mean, unless you're letting there be collisions between like things that shouldn't overlap, you have the same number of.
Possible different unique representations.
No, because if you reuse one of those buckets again, you would have a lot of collision with some other number. You wouldn't be able to tell the difference at all.
But I thought he was asking, assuming no, like if you restrict to no collisions.
I mean,
Same amount.
yeah.
Of, yeah.
So
but
the fact that they're laid out in that order is independent from the
No, it isn't.
like.
But suppose you could have a couple of bits of collision. That wouldn't help you in the old scheme. You're still restricted because they have to be contiguous.
Okay, but it's not the fact that they're continuous. It's that the fact that you're allowing collisions. And
No, it is because with contiguous you can't have you wouldn't be able to allow.
that's not the reason, though.
You can do the same thing.
They are tied together.
They both have they both lead to a constraint. So if you don't allow collisions, you're restricted. If you're visually contiguous, you can't allow collisions.
Let me reword it. He asked if we were not being efficient because we were laying it out in a way that made sense, like to look at. But if we had instead implemented it so that we randomly selected them, but with the exact same properties as the old scheme, so that we never allowed collisions, then it wouldn't be laid out, but you would have the exact same properties. It wouldn't be any more efficient in that
Correct.
case. It's the fact that we're now allowing collisions and going beyond the normal range.
Correct, but the other side of it is you couldn't allow collisions
Correct.
if they were visually contiguous.
Yeah. I kind of view the adaptive one as a generalization on the fixed one, like conceptually, because the fixed one is basically the RDSE with a collision tolerance of 0, and if you increase the collision tolerance in terms of how it performs, or in terms of what it does actually, it's just visually not the same, but in the background it is doing the same things. So RDSE, I would say the basic scalar encoder is the RDSE with a collision tolerance of 0.
Okay. All right. Cool. No, that makes sense.
Yeah.
That's a good one.
Yeah, and then, but there is one caveat to that, which I wanted to ask you guys actually, is the topology of the representations, will that affect certain kinds of problems like vision or something? Will the basic scalar encoder
you
be
can,
better?
Well, you can't use this scheme with if there's a topology. You can't, every bit is not equal anymore. So, it's restricted to cases where you can't have, where topology is irrelevant.
So in a hierarchy,
well, I don't think topology is tied to
in a hierarchy. So then it's like I'm imagining a hierarchy where you have only local connections.
Correct. So you have topology
That's
there,
topology,
and then
yeah.
you wouldn't use this scheme. You couldn't use this scheme, yeah.
Okay.
At least I don't know how you could. But you wouldn't have a scalar encoder there anyway. You'd have a visual input or auditory input or something.
Why couldn't you have a 2D index?
Maybe there's a way to extend it so that you maintain all the overlap properties in the topology. But with topology, you also have adjacent columns represent slightly have a center that changes as well. So you have to take that into account as well.
Would lose it immediately.
Yeah.
Okay. But
So maybe there's a way to do it. I don't know.
code it, but I don't think you could.
It's
you
not
would have to then specify which connections went where to the SP
Yeah.
and everything.
And also in that case, does it really buy you anything? At that point, you're not dealing with min-max issues.
we implemented wrapping in RDSE?
No. That is an option in the Scalar Encoder, so that may be, is that an option in the Scalar Encoder? I think so. That may be another reason to still use the Scalar Encoder.
I mean, we could use it.
Yeah, with wrapping, the RDSE doesn't buy you anything. Yeah, so that may be another reason to still use the Scalar Encoder.
Wrapping?
Wrapping, yeah. Like if you, like time of day, for example, you want 23 hours to be treated similar, to be similar to 1 a.m.
Okay.
So we have a circular representation.
Yeah.
So that's a good point. That's another reason to use Scalar Encoder.
Yes, that is. Unless we can find a way to move two buckets, to generate buckets from two different sides towards each other and meet in the middle somehow.
We could, but would it buy you anything at that point?
Well, it would buy you a.
You need to know the ranges.
Yeah. But I mean, with the Scalar, with the RDSE, if you can generate buckets as needed and not have to traverse the thing, which you would only be able to do if you had this meeting in the middle kind of idea, it would buy you efficiency of memory storage. If that's possible to do. And then you could do wrapping with that as well.
Yeah, I think if you're doing wrapping, then I don't think RDSE buys you anything. It's not like you
because you know the edges.
Yeah, exactly. You have to know the edges.
Okay, that's true.